we have also with us Mr. Sean Meyer Steele, who's the president of CaribDA. And our guest presenters are Mr. Jerry Matteo of Water Tech Sales and Consulting, Inc., based in Puerto Rico, Mr. Jess Salvador of LG Water Solutions, and Mr. Nathaniel Nate Weeks of LG Water Solutions, LG Chem. And so we would like to welcome you and thank you for you so willing to share with us your knowledge for those of us in the water sector. And about half of CAWASA's membership are involved in desal, either distribution or water. Their main source of water would be desalinated water, particularly in the northern islands of the Caribbean. So I'm going to hand over to you. Now, Jerry?
Yes, we're ready.
And again, I should say this is number 15 in our series. And we have been doing that to keep our operators, at least we try to keep them busy virtually. And as you indicated before we started, that we all are becoming experts on using and being more efficient, perhaps, using the virtual platforms to help to educate and inform our operators around the region. So over to you, Jerry.
Okay, thank you very much. And thank you to CAWASA for having us participate, having CaribDA participate. I'm going to pop our presentation up here.
Everyone see it?
Yes.
Yeah,
okay.
you.
Yes.
Right.
Okay, so Ignatius already gave a little introduction. I'm Jerry Matteo. You can see me right there. And we've got Jess and Nate with us also. So you probably know me a little bit better. I think I've been involved in a couple of CAWASA conferences in the past. I was at your last operator session in St. Lucia. Jess travels throughout the Caribbean and visiting customers. You know, LG is the same LG company you're used to with the red dot that sells great TVs and everything else, but it's a huge company. I believe there's like 200 or 250,000 employees in LG. And part of what they do also is chemicals and other things. And within the chemical division, I believe it's within the chemical division, is their membrane operation. So they make membranes in South Korea and have membranes all over the world, including in the Caribbean. And I don't know if Nate's a member also of CaribDA. If he's not, we'll get him to be one. So we're wearing, all of us are here today, I think are wearing a couple of hats. We're here today with our CaribDA hat on, but we've got our companies that we work for also. Okay, let me get this to go. There we go. Oh, it took so long. So a little bit about CaribDA. You could look up our website, CaribDA.com, and it's formed in 2007. So it's one of the newer organizations in the Caribbean. I don't know how old CAWASA is, but I'm sure we're younger than CAWASA. And, you know, the name implies desalination, but also part of our mission is to promote and develop water reuse also. So we do get involved with wastewater reuse and other types of water reuse. We have heading toward 250 members. We have our conference every 2 years, and we had to reschedule this year's because of COVID, obviously, rescheduling it for next year in the Bahamas. And I know we've got some Bahamas guys on this conference today. We're also affiliated with some of the other desalination associations, IDA, and I'm not sure, I believe in some form or fashion with AMTA also. So today, we're gonna really, I guess, have a little bit of an introductory discussion to reverse osmosis. Now, I know some of you guys, I just saw the list of who's on the call, actually run systems. And I think what you'll get out of today is maybe more of the theory, because you already know the application part, you're doing that every day. And then some of the guys that are in potable water or wastewater, this might be new to you. And I find it really interesting. I also find that it's hard to get this on the first pass. I've seen this kind of presentation a couple of times, and you get more every time you see it. So we'll do the best we can going through it fairly quickly. And at any point, anyone, you can ask any questions, and one of us, Jess, Nate, or myself will answer. I guess I should say a little bit about Nate. Nate is an applications engineer, so he's very technically oriented. Jess, I believe, is a chemical engineer, also very technically oriented. Jess is the regional manager. His territory covers the Caribbean. Both of them, because I've worked with them on different applications, really know a lot about these, about reverse osmosis systems, not just the membranes, how to apply them, how to design a system to use them properly. And that's some of what we're going to talk about today. I'm going to handle this first part, the introduction part, these first couple of lines, and then Nate will pick up on the design considerations. You may or may not have seen this slide before. It's shown in a lot of conferences and papers, especially when speaking about reverse osmosis. And it looks complicated, but really all it is. So down here, I don't know if you can see my little cursor. I'm trying to use my cursor like a pointer. So down here, we've got a table of microns. You know, here we got 1 micron and 10 microns. If you deal with reverse osmosis, out in front of your system, you've got some pre-filter cartridges, and those are in this range of 1 to 10 microns. And we're trying to show here what type of technology, what different technologies remove from the water based on the particle size that we're trying to remove. So way over here on the right at the top, we've got particle filtration. Probably everybody on the call is familiar with media filters, just sand filters or multimedia filters. They're used in all kinds of applications, including surface water. And below that, you'll see the kind of the size particles that a particle filter, the media or particle filter would take out. So you could see down here human hair. So something, the diameter of a human hair would come out in a particle filter. Carbon particles would come out. And we even start to get into some bacteria and things that would be filtered out with just a standard media filter. Then we get into microfiltration. Where's my cursor? Lost it. There it is. So microfiltration is finer, and it's going to take out, you can see it's getting down closer to 1 micron. It's going to take more things out of the water, including bacteria. Then we get over to ultrafiltration. Ultrafiltration is really good for particle removal. It doesn't remove dissolved solids. We're going to get to that here in a second with these two, but it removes particles really well, doesn't foul very easily. And ultrafiltration is used in the last several years a lot more in turbidity removal applications, river water and surface waters. It's also a good pre-treatment we're going to find for reverse osmosis. And over here to the left, we've got nanofiltration and reverse osmosis. So these are more the technology you're thinking about when you think about desal, especially up here on reverse osmosis. And really, you can see we're going to now be able to take out dissolved solids. So if we had a dissolved solid, if we had, it's just exactly what it says, solids dissolved in water. So if we had a glass of water in our house and we started to put salt in it and stirred it, we would dissolve that salt. If we would evaporate the water away, the salt would come back in a solid form. So dissolved solids are simply these different minerals and compounds that are dissolved in water. So reverse osmosis will actually allow us to pass water through a membrane and have pure water on one side and leave the salts on the other side. And that's why we use it in desal for potable water and other uses, so we can drink the filtered water and discharge the dissolved solids. This is kind of complicated. I'll just leave it up here for a minute. Not complicated, just has a lot of info on it. So here we've got across the top micro, ultra, nano, and RO. Microfiltration, ultra, nanofiltration, and RO. And then just really kind of another way of showing what I was just talking about, showing the yeses and the nos and the percentages of what each of these type of filters would take out of the water in this realm over here. In dissolved solids, calcium and magnesium, which we know is hardness, sodium chloride, which is salt, like I just talked about, table salt or salt in seawater, You'll see here, so in those, micro isn't going to take any of those out. Ultra's not going to take those out. Nano takes a lot of it out, but not all of it. And RO takes almost all of those items out of the water. None of the technologies filter out gases, not carbon dioxide gas or hydrogen sulfide gas. And so that's, and this actually relates to pH. Those of you that run a reverse osmosis system know that your filtered water, which is called permeate, is low in pH. And part of the reason, I believe, is because carbon dioxide gas does pass through the membrane into the permeate water, and it forms, is it carbonic acid? But it forms,
Carbonic acid.
okay, carbonic acid that would make permeate a little bit acidic. And so a lot of governments and users of RO add back some minerals, sometimes calcium or even lime, something to raise the pH back up. Some don't. If you don't, it can be a bit corrosive to permeate to your distribution lines. So here we've got dissolved organics. This would be like tannins and dissolved organics. Maybe your water's coming from an area with a lot of vegetation and trees and things. Those natural organics can be removed to a high degree by both nano and RO. Colloids, that's particles, real particles. UF, like as I mentioned on the previous slide, does a great job of taking out particles, but up here, if you see at the top, it does not take out the dissolved solids. Bacteria, they all do a pretty good job on that, and viruses. The further we go to the right, the better we do on viruses. Nanofiltration, you don't see a lot. I sometimes hear it called like a membrane softener. I do have some customers that have nano in industrial applications. So it doesn't take out everything that an RO does, but it takes out, look, a lot of the hardness, a lot of the dissolved solids, and a lot of the salt, the sodium chloride. So it can be used in a lot of applications. Probably would be a bit salty to drink this water. So we're not using it for potable very often, but it has its benefits, and it would use less pressure. You're going to see later. It would use less pressure than an RO. Okay, I like this slide, even though there's a lot on here. So sometimes you forget that these terms we throw around, maybe not everybody's familiar with the acronyms. So NF up here is, again, nanofiltration. BWRO, that's brackish water reverse osmosis. And SWRO, that's seawater reverse osmosis. So I think most of the people online today on this webinar that have a membrane system are probably using seawater RO. But we've got a lot of customers throughout the Caribbean that have industrial users primarily that have brackish water RO systems. And I like this right here, content, because this is also doubled as a good definition of what is seawater and what is brackish water. So in the industry, we throw those terms around, brackish and seawater, brackish and seawater. So brackish water really is up to about 10,000 milligrams per liter of dissolved solids. Above that, we're getting into seawater, what we call seawater. So you would normally have wells around the Caribbean. I find this says like, okay, I think up here we show where would this water come from? So these lower dissolved solid streams would primarily come from well and surface water sources. This really high dissolved solid is obviously the ocean, right? And a well near the ocean might fall in this category here, this medium pressure brackish water RO, or 10,000 milligram per liter dissolved solid, because I've seen that a lot, and you may have seen in your own experience, wells along the ocean have seawater intrusion from underground sources, and you're bringing in some seawater into the well. Lost my cursor. Okay, and we're going to find later as we talk more, we're going to need more pressure as we go toward this right end to separate pure water from the dissolved solids. We're going to need higher pressure when we run our membrane system, and we're going to, I think, explain why. Oh, this is kind of interesting. So rejection. Rejection is what doesn't pass through. I think Nate's going to get more into these terms. So you've got your feed water going into your reverse osmosis system. The water that passes through our membrane, that's our product water for drinking or whatever purposes, is our permeate water. the remaining
I didn't know it was on the floor. I apologize.
the remaining stream that has all of our concentrated dissolved solids in it is called reject or concentrate or brine. And we'll be discharging, let's see in this percentage. Got this wrong. Okay, so what rejection is here, this is what we don't pass through the membrane. So this is the percent of what doesn't pass through the membrane. So you're going to see here that over here on reverse seawater reverse osmosis and brackish water reverse osmosis, almost everything passes through the membrane and is rejected. The dissolved solids are rejected by the membrane. That's what this means here. So 99, 98, 99% of the dissolved solids are rejected by the membrane. They stay in that concentrate stream I was talking about. They don't go through to the permeate. This last little thing down here is interesting. I think we'll get into this later. As we move up on this scale of higher dissolved solids, we're going to need higher pressure to separate the pure water from the dissolved solids. And as a rule of thumb, we need about 1 psi for every 100 milligrams per liter or parts per million of dissolved solids. And you're going to see that, I think, a little more as we go through. Okay, so this is a cutaway of a membrane. If you saw a membrane in the field, you obviously wouldn't see this cutaway here. You just see this cylinder. And normally there's a hard fiberglass shell here. So you would see this anti-telescoping device here on the end. It's like a plastic circle, honeycomb circle, and this big fiberglass cylinder. But what's inside of it is what's important and is the key to the technology. Membranes, you're probably in municipalities, especially in ocean desalination, going to see pretty much the standard membrane, which is, looking for my cursor here, where is it? Oh, there it is. Which is 8 inches in diameter and 40 inches long. That's pretty much the standard. There's other sizes out there, but that's pretty much the standard we're going to see in the Caribbean. 8 inches by diameter by 40 inches long. In some smaller applications, primarily industrial, you'll even see 4-inch diameter membranes by 40 inches long, and even 2.5-inch diameter membranes by 40-inch by other lengths, actually. But the standard you're going to see, most of you, is 8 inches in diameter by 40 inches long. All right, so what's really going to happen when we have these membranes, because there'll be a lot of them, installed in our seawater or brackish water RO system, we'll drive feed water through some spaces between our membrane sheets. We'll drive feed water right through here, through the spiral, not through the center. The feed water will go right on through and come out here. Remember, I was using this term called concentrate. It'll go right on through. But while it's passing through, pure water molecules, H2O molecules are going to pass through the membrane. Let me see which one's the membrane. This is the membrane. Here's a membrane and here's a membrane. They're folded sheets. H2O molecules are going to pass through that membrane. They're going to go in a spiral all the way around to the center tube and pass out as permeate. And they're virtually going to have no dissolved solids, no bacteria, no viruses, pretty much everything, all those things I just mentioned are going to remain in this concentrate stream and go on to the next membrane. But pure water molecules, pretty pure, 99, 98% pure, are going to end up in this permeate stream, and that's our product water that we're either going to drink or use for some other purpose. This doesn't show it, but a membrane system is going to have multiple membranes in a series. You're going to see, most of you in desalination are going to see 6 or 7 membranes in a series. So I always find this interesting. I think Nate will get into it more. The next membrane over here to the right doesn't see feed water. It's going to see feed water minus the pure water that got pulled out here. It's going to see a higher concentration than the first membrane. And the second membrane is going to, the third membrane is going to see even higher than the second, and the fourth higher than the third, et cetera, et cetera. And most desal systems that you're going to see for municipal drinking water purposes are going to have 6 or 7 of these in a pressure vessel. So that last membrane is going to have almost double the dissolved solids of the feed. And that's one of the reasons why we're going to need higher pressure than the theoretical pressure that we would state we need for seawater. We're going to need higher pressure than that, because we've got to, when we get down to that last membrane, we're actually desalinating much higher concentrate water. It might not be a little clear. Hopefully it's clear as we go through the other slides. And that's why I also said right at the get-go, it really pays to see this presentation more than once. Okay, so we're going to look at the RO system itself now, I believe. Oh, we're going to look at the theory of reverse osmosis. So this slide, boy, you could look at this a lot of times, and it looks simple, and sometimes it looks complicated, and sometimes I don't, when I first look at it, I say it doesn't make sense, but it is what happens. Here to the left, we've got a diagram illustrating what happens in the natural phenomenon called osmosis. We're here to talk about the technology, reverse osmosis, but it's based on a natural phenomenon called osmosis. And that is that if I've got a membrane, I hope you can see my little arrow. If I've got a semi-permeable membrane separating two streams, so this membrane here would allow, in this case, let's just say it lets water go through, H2O molecules go through, but it doesn't let anything else go through. If I had this membrane, my cursor, every time I take my finger off, I lose my cursor. Okay, here we go. If I had seawater, let's say, or a salt solution on one side and pure water on the other side, and I just let it sit there with no applied pressure, pure water would actually pass in this direction into the seawater side or the salt side. It would not go this way. It would go right to left, the water molecules. And the reason is the water, the natural phenomenon is that, this solution over here will try to naturally equalize with this side in terms of concentration. So it's more concentrated right now than the right side. The only way we can dilute it to be equal would be if we pass more pure water molecules on this, through from the right to the left and start to dilute the salt water or seawater on the left side. And I use this little example of a slice of fresh potato. You take a slice of fresh potato and drop it into a glass of salty water, you'll see that the potato slice shrivels up. And what's happening is really osmosis. Fresh water in the potato is exiting the potato slice into the salt water in your glass, trying to equalize that salt water. It'll never get there, but it's trying to. And in the process, the potato slice shrivels up. So it's not really salt. We always think, oh, when you see something shrivel up and dry like that in salt water, we think that the salt is entering the potato. No, it's the water, fresh water in the potato going into the salt, trying to equalize that solution. All right, so reverse osmosis is simply using this natural phenomenon to our advantage by applying a pressure, and we're going to do it with a high pressure pump on the high concentrate side. In your case, or our case, it'd be the seawater side, to push that, where's my cursor there? To push the water from the salty side through the membrane into the freshwater side, opposing the natural phenomenon of osmosis, opposing it with pressure. And, oh, someone's putting a cursor on there, I see, some red marks. And the pressure that we need will be directly related to the dissolved solids. So seawater needs a lot more than a brackish water. We saw that in some previous slides. Seawater needs a lot more pressure than the brackish water system. I also find it interesting. It does not matter what the makeup of the dissolved solids are. So the dissolved solids can be very high in sodium chloride, which we know is table salt, could be very high in calcium, could be very high in manganese. Doesn't matter what the TDS is. This phenomenon of about 1 psi for every 100 milligrams per liter of dissolved solids holds true no matter what those dissolved solids are. I think what's coming next, let's see, is like a little graphic, yes.
Animation.
Right, a little animation, thanks. A little animation that's going to show that, and I'll just rerun it. So we're seeing that we've got, this is osmosis, not reverse osmosis. This is osmosis. Let's go back. We've got a semi-permeable membrane just sitting there with no pressure on either side. And what's going to happen is fresh water on the right is actually going to pass through to the salty water on the left, trying to equalize the concentrations of the two solutions. I've never seen this particular animation. I really like this one. Okay, and that pressure that builds up. I guess I didn't point this out so much in the other slides, but you obviously are going to build up a pressure here, right? Because look at these difference in levels here. That is the osmotic pressure. And that's the pressure we need to overcome with a pressure pump if we're going to drive this seawater the other way and make fresh water out of ocean water. Now we're going to see the same animation with reverse osmosis. Okay, so in this case, we are applying a pressure. That's my big red arrow. So this is a mechanical pressure that we've got to apply with a pump. And we're going to actually we're going to overcome that osmotic pressure, and we're going to force fresh water from our salty solution through the membrane in the opposite direction to create our pure water for drinking or other purposes. So this water on the right is what you're going to sell to your constituents or supply to your customers to drink or use for whatever other purposes. This concentrate, in the case of ocean desalination, we're just going to pump right back to the ocean. And I think Nate's going to get into it. This concentration of salt, after we've driven all that we can through a membrane, is about twice of the original concentration. So we started out with 30,000 milligrams per liter of dissolved solids in ocean water. Our concentrate is going to probably be 50 or 60,000 milligrams per liter of dissolved solids that we're going to put back to the ocean. And over here, I think you're going to end up with what I see around the Caribbean, like you don't have zero dissolved solids here. You probably have 300, 400, 500. I don't know if that's microsiemens or parts per million, but you do have some dissolved solids in here, primarily a little bit of salt. So sometimes you might even taste that. You're probably used to it in the countries you live in. Like a visitor might come in and he can note it because he's used to drinking something else, but there is a little bit of dissolved solids left in this water. But we've removed the bacteria, the viruses, everything, all the other contaminants, and almost all the dissolved solids. This is just another illustration. Oh, I must have put these red lines on here when I move my cursor. Okay, so this would be, this white line in here is our membrane, this white horizontal line. We're showing our feed water coming from the left. Let's just say it's seawater. Remember, it's going right on through membrane to next membrane to the next membrane until we dispose of it back to the ocean. But all the time we're doing that, we've got water molecules going through the membrane to our permeates. Excuse me, to our permeate side. So we've got water molecules, H2O going through, all the salts continue on down till we discharge them. This is called, I believe, cross-flow filtration. So a multimedia filter, I believe, is called direct filtration, where we're just filtering straight on down through the filter. And here, we're actually, even though our flow's this way, left to right, horizontally, we're filtering perpendicular to the membrane. So it's called cross-flow filtration. And really, reverse osmosis is just it's just a filter, just a super fine filter, where we can take dissolved solids out of our salty stream. Okay, so here's some comments here. So ionic, that's just our positive and negative. I think we're going to get, I think we have another slide that's going to show us this. So this is just all the different compounds in water: calcium, sodium, chloride, magnesium. I think there's boron, lots of other things in there. And what's the reason this reverse osmosis works is that anything with a high molecular weight is rejected by the membrane. So almost everything is rejected by the membrane except H2O. Okay, I thought there was going to be a slide that showed us some of the ions, but not. Okay, I guess I should say, let's go back. Any questions so far from anybody? I'll go back on some slides if you want us to. No? Okay. So the next is a little slide about, thought we were going to go into, okay, we're still in RO system. Okay, so down here on the bottom, this photo is what a fairly large reverse osmosis system would look like, right? So these, I mean, this is very elementary for those of you that are already running RO, but for some that aren't, these questions, I'm only mentioning this because probably when I first started, I didn't know some of this. So these vessels we're looking at here are not the membranes. That is the pressure vessel. And inside that pressure vessel are our membranes. So up here is our membrane, what it looks like, you know, when we don't tear it apart. Here above it, the top photo is if we would unroll the membrane and we look at all the different membrane sheets and all the different, I didn't get into all the details. There's a lot here. There's spacers and different things, but the key to that technology is the membrane itself. It's one of the sheets inside this arrangement of different sheets, rolled up inside this shell, you know, rolled up inside into the 8-inch by 40-inch configuration, fiberglass with a hard shell, loaded inside these pressure vessels. Here's just a pressure vessel. It's showing you a cutaway with, I think that's a piece of a membrane in there. And a bunch of the membranes, like 6 or 7, are lined up in the vessel. And you can see we've got to have a lot of these if we want to make a lot of water, right? So what we would do, we would feed water into all of these membranes at one time. And our feed water would just travel from left to right. While it's doing that, we would have this cross flow filtration through the membrane where we're driving water molecules through to our permeate side, our product water side. Our concentrate would just continue right on down to the end, and then we would discharge that. You could see here, so I've got this one group of membranes here, or pressure vessels here filled with membranes. There's another one here to the left. These are called trains, so we would have many of these trains to make up, to create enough capacity for us to produce the amount of water that we want to produce. And these could be shut down, so you could shut down a train while you're running the others. You could clean a train. You could replace membranes. You could do maintenance while the other trains are running. So part of a system is obviously the membrane elements. The pressure vessels I just showed you, these white, they're like a composite, like a plastic. Obviously, they can handle high pressures that we need, 600 or 800 PSI in seawater. The skid, so they're calling this a skid, but it's sometimes referred to as a train. The pump, we're going to need a high pressure pump. This is it right here. If you can see my cursor, we're going to need to create that 600 or 800 PSI to overcome the osmotic pressure and filter pure water out of our salt solution. An energy recovery device, I wasn't going to get into this too much here. I don't know if Nate is, but the real expense on reverse osmosis, especially desalination of ocean water, is electricity to drive these high pressure pumps. And so there are devices where remember we said we're going to discharge that concentrate out the back end, or it's under pressure. So we would be throwing away energy if we just discharge that straight to the ocean and not try to recover some of that energy. So there's devices out there where we run that concentrate through a kind of a mechanical interchanger and boost up the feed pressure with some of that waste, about to be wasted pressure energy in the concentrate, and we can reduce the size of our feed water pump that way and reduce our electrical consumption. Oh, by the way, if I could put a little pitch in here for CaribDA, on our website every month we're posting a presentation just like this one. Some are more technical, most probably are more technical, all different aspects of the technology. And at times we might put up one on energy recovery. So you can tune into our website. There's a section called Publications Resource Center, I believe. I think it's really easy to find down on the left side of the website, and you'll see that month's presentation. It's up there for the whole month. I believe you could even download it and save it. We've got them lined up all the way through January. What we're doing is going into our archives. We've got workshops and conferences and different presentations stored in our archives. We're going back in there rather than have them just sit and collect dust, and pulling out ones we think are attractive to our clients, our members throughout the Caribbean, and posting them. So you can take a look there. And I mentioned that because this energy recovery device, I know we have some on energy recovery devices. And also we were looking for suggestions. So if there's a device, if there's a presentation you want to see, let us know me, Jess, Nate, or Nate, somehow get the word to us, and we'll post that on one of our future postings on the website. Obviously, we have got a lot of piping instrumentation, and I think we're going to talk a little bit about pre and post treatment because that's important. All right, we're getting into that. So the RO is designated by this rectangle in the center here, right? And I mentioned the feed pump several times now because we need pressure to overcome that osmotic pressure to make this whole thing work. But to the left, we need pre-treatment. And this is really important because if our membrane is so fine that it's going to actually filter out, only allow water molecules to go through and not allow dissolved solids to go through, it certainly cannot handle turbidity and particles or other things like that. So we've got to take all those things out through pre-treatment. If we don't, we'll foul the membranes right away. So pre-treatment can be a number of things. Actual clarifiers. So those of you that are in surface water, maybe you're running clarifiers or even wastewater. Sometimes the big, some of the very large desal systems in the Caribbean around the world actually use clarifiers to first take out sand, obviously, in seawater and other colloidals that would foul our membrane. So we could use clarification. We almost always have multimedia filters, and like I think I mentioned earlier, we can have ultrafiltration or even microfiltration, and we almost always have cartridge filters to remove particles before they ever get to our membrane. And in spite of all that, we often use an anti-scalant so that whatever might be left in the water that's undissolved will flow through the membrane more easily and not foul. And the anti-scalant helps us do that. So that's on the pre-treatment side. On the post-treatment side, I think I remember I mentioned that we sometimes post-treat to boost up pH, and calcite really is just calcium carbonate. Calcite's used for that application a lot, and so is caustic soda, sodium hydroxide. Chlorine is obviously another disinfectant. Even though we remove most of the bacteria, or almost all bacteria and viruses, we've got a long way to go to get to the consumer. We're going to be sitting in storage tanks, clear wells, piping. So I think most utilities add chlorine after. Jess, why do you add ammonia? I don't know that.
Well, ammonia is normally added,
pH?
In the post-treatment, but most of the time it is utilized on, for brackish, application, especially in the United States, where they would like to have, chloroamine instead of straight chlorine for disinfection. So combining ammonia and chlorine gives you this chloroamine, and it becomes like a chloroamination process,
Right. So that's another disinfectant, but it has less effect on trihalomethanes to create those compounds, right?
Yes.
Let me ask a question. I don't know, hopefully everyone's tuned in. I don't know if your mics are on or, I see all the mics are turned off. Maybe they can't even answer, but if someone can pipe in that's running an RO in the Caribbean, or is anyone using on this pre-treatment side? I see all the mics are off, so someone have to turn on their mics. Can someone just speak up what type of pre-treatment you're using on your reverse osmosis, on your desal system?
Yeah, you're free to unmute if you wish to ask a question.
Yes, it's mostly cartridge filters for us, seeing that our water is from deep wells, so the SDI is less than 5, so only cartridge filters we'll need. That's here in the Bahamas.
That was a great point. Well water, it's usually really low in particles. And I didn't even think about that. So that's a good point. You don't even need a media filter there. That's really good. So you're in the Bahamas. So do you also have, so are all of your ROs running on wells, or are any running from like ocean intake?
No ocean intake. We do have some that's brackish that comes from, let's say, more shallow wells, like maybe at like 50 feet down as opposed to 150 feet down. So those tend to be more high in, not dissolved solids, but suspended solids. So we do have some brackish systems that we have that operate at about 400 PSIs, but mostly everything is well. No surface water, salt water intake.
Okay.
Mhm.
Let me ask you another question, because while we're on this subject, so right here on this left, as you can see my cursor when I'm talking about pretreatment, cartridge filters are disposable. So, you know, y'all don't dispose a clarifier, you don't dispose your multimedia. I mean, you do backwash it, and every now and then, every so many years, you change media. You don't dispose ultra and micro. But cartridge filters, they're like, what would you call them, sacrificial? You want them to foul and throw them away before you affect your membranes. So this person that was just speaking there from the Bahamas, your real clean well water, do you have to change your cartridge filters very often or no?
We do, no, not if the water that we're getting is of good quality. Now, we do have a plant that's currently experiencing some oxidized iron that we have to go ahead and change out the cartridge filter every other day because they're getting clogged.
Oh my God.
Yeah.
That's a lot. Yeah, that's another great point. I'm glad I started to stimulate some questions because remember, I don't know, it's so much to catch on one pass, but iron and manganese particles, iron and manganese and aluminum, if you have aluminum in your water, they foul membranes very, very readily. So they've got to be removed. And there's different ways to do it. There's other kind of filters too that remove iron and manganese. And wells, we just said they're really nice and pure, usually in terms of turbidity, but a lot of times they've got iron and manganese down there. And so thank God, at least your cartridge filters are handling the iron and manganese versus your membranes, because your membranes.
Exactly.
And a cartridge filter is like maybe 10 or 15 bucks, and a membrane is like 500 or 600 bucks. So
exactly.
US, that's US. All right, are you adding on your post-treatment? Are you adding any of these things for your post-treatment?
Post-treatment is just calcite, calcium carbonate, and then it's chlorine. That's
Okay.
the only post-treatment that we're using.
Good. And your calcium carbonate is just calcium carbonate, it's just calcite filters, right? Just filters?
Yes, just calcite filters. Yeah, calcite tanks that we use.
Yeah, that's right. So what that is just a filter vessel. If you looked at it, you'd think it's just a regular old filter in there, but it's full of these really it's like, looks like gravel. It's full of calcium carbonate little rocks.
Yes.
And slowly dissolve as the permeate flows over it. They slowly dissolve, and then eventually you have to refill your filter. All right, excellent.
Exactly.
Thank you. Thank you for the input. We don't like to just be the only ones talking, so I appreciate it. And
Not a
really, it
problem.
helps to have someone out there really doing this to give us input. And if we're wrong, if I say something wrong, pipe in also. Okay, let's move to our next slide. I know we got a lot of slides. All right, so this is just another illustration of pretreatment, and this is not all the pretreatments by any means. So they don't actually even show our RO on here. Our reverse osmosis system would be way to the right. That would be process. But we're showing, we would have screens if we're coming from a surface water. You might even flocculate if you have a clarifier. Different types of, we might use coagulants, different types of filters. Oh, this is important. Membranes, the type most of us use, polyamide membranes, do not tolerate chlorine. Remember, we're adding our chlorine after the membranes, not before. But sometimes we have chlorine in our water. For example, some bottled water companies actually take city water and then they run that through reverse osmosis systems and make bottled water from it. In those cases, we've got to remove the chlorine. If we don't remove the chlorine, you will oxidize the membrane, you will open up the pores, and instead of just H2O molecules passing through, some other bad stuff will pass through. So we do not want any kind of oxidizer on our membranes. We don't want chlorine, we don't want ozone, we don't want, what's another one I've seen people use? I've seen people think because ozone's a great disinfectant. I've seen some industrial customers, they might be disinfecting their tanks with ozone and they think they can disinfect their RO and they will ruin the membranes right away. So you don't want any oxidizers on the membranes. Let's keep moving on. This is the slide I thought we had earlier. This is a lot of data here, but I think Ignacio said you're going to get this later, so you can look at this later, and you're welcome to ask us, get to us through emails later, because I don't want to spend too much time. I know there's a lot more slides to go through. So I think to the right, we're showing, this would be ideal if we had what I'm showing on the right, this would be ideal feed water for our RO. Low in suspended solids. STI is called silt density index. What I always think of that is like it's silt, but it's the kind of the test for it is how fast water, your feed water filters through a little apparatus. So you want that low, you want turbidity low. Remember, iron and manganese, killers. Even the fellow just speaking said his sacrificial cartridges are getting fouled by iron and manganese. We want that low. They're really putting a low number here. I think we can maybe tolerate a little more than that, but that's good. Hydrogen sulfide, I don't know why they have it so low. I mean, I've seen some systems. What will happen is the H2S will just go right through. Maybe that's what they're saying. So the hydrogen sulfide gas is going to go through the membrane. It's not, the membrane is not going to remove gas. We want low organics. We don't, you know, you could see. pH, the membranes you can see are tolerant to a real wide range of pH, and we want really low chlorine. And I guess we can't be super high in temperature, but this is really high here, 45 degrees C. This is just more of the same, just in a different format, all about pretreatment. And you know, we could do a whole presentation on pretreatment. It is, to me, one of the keys to your RO running really, really well. The other that Nate's going to talk a lot about, I don't know if he's going to get into some of this pretreatment, but you've got to also design your RO system really well. But sometimes the focus is on the RO system and the pretreatment is a little bit of an afterthought, and that could be a problem later because the pretreatment is equally important as the correct design of your RO. Really, really is. Again, because the membrane is so fine, we don't want, we can't tolerate these other things that would foul. We want them to come out before the membrane does its job, which is separating water molecules from dissolved solids. So I won't dwell on this one. You could look at that later when the presentations come out back to you. I think that's my part. So I think we're going to have Nate next. Now his presentation gets pretty technical. So, you know, don't be disappointed if some of it seems like, you know, maybe even, you know, like it's like going back to school. Why do you have to learn some of this stuff? But it's really, you know, doing math in high school. I'll never use this, and you find out you do use it. But it's really,
no quiz at the end. It's
really, really worthwhile. There's Nate. And you know, a lot of times your suppliers do this for you. The builder of your RO does this for you. Your membrane guys like Nate and Jess, they'll do all this for you. They're going to run through a lot of this calculations for you and math for you, but it really helps to understand it. It actually helps you run your system better, in my opinion. So again, this is some of your first time seeing it. It's going to be I've looked at his slides. They're pretty technical, but you know, you can ask questions later at the end of this or through emails, and we'd be happy to help you. Okay, so I'm going to hand over to Nate. Nate, I don't know, you control the presentation from there?
I was thinking you've got control, so I can just give you a thumbs up on screen when you need to progress slides.
Very good.
Does that sound good?
Yes.
Okay. So just going to introduce myself real quick. So like Jerry mentioned before, my name is Nate Weeks. I'm an application engineer with LG Chem, and we're a membrane manufacturer. So my responsibility is to support the sales team. I perform membrane projections and customer trainings, and we also work on new product development, manage pilot studies, and do some forward-looking data analysis to forecast new products and see how we're performing. So I'm going to go through some factors influencing RO design today, starting with some basic terms, system configuration, talk a little bit about our software, and then product selection. And again, like Jerry mentioned, stop me at any time. This is a lot of numbers in this presentation here, but you know, these are what we like to think about as manufacturers is sort of giving our clients the tools to eventually run these projections themselves. So this is sort of a first step to learning about the theory. So first of our terms is RO recovery, which is the percentage of feed water that will become product water eventually. And it's calculated by dividing your permeate flow by your feed flow. Basically, this is a number that a client targets when they want to calculate their water savings and environmental impact. So increasing your recovery obviously decreases the concentrate flow rate. You're saving more water by making more product. And it increases the feed pressure because, as Jerry mentioned earlier, the concentrate from one element inside a pressure vessel is being fed to the next element, and that will be a higher concentration, and that process will continue to scale up as you move down a pressure vessel. So if you're recovering more water, you're going to have more saline more salty feed water at the end of your pressure vessel, it's going to require more pressure. And it also increases the risk of scaling, because as you, sometimes they say cycle up that feed water into concentrate that's more and more salty, you're going to have higher saturation of your dissolved solids. So the more recovery you have, we're operating within recommended ranges. You need to be more careful about your anti-scalant dosages and things like that. But this is one of those parameters that we get a target from a client, and we really want to hit this because these are the metrics that municipalities care about for environmental impact, and it's just an indicator of a system that's well designed if you can recover a good amount of water. So here's the basic calculation for recovery. As you can see, we got 440 GPM feed and 185 GPM permeate, comes out to 42% recovery. So that's like an average recovery for maybe a seawater system is just under 50%, probably a single pass, higher salinity. That's going to be right where in that range. So our next term is flux, which is the amount of water that's passing through the membrane area per unit time. So it's expressed in gallons per square foot per day, or GFD, or liters per square meter per day, or LMH. And this is one of those things that oftentimes is set by a client, but this is a parameter that is really influenced by the type of water that we are getting from the pretreatment, like Jerry was just talking about. So there's a question about what micron filtration we would want ahead of our filters, and it's really important from an engineering standpoint. From a design standpoint, we want data about SDI, like Jerry mentioned, silt density index, because that sort of sets our parameters for how aggressive or conservative we need to be with flux. We might need to tell a customer, oh, you need to purchase a couple more pressure vessels to decrease your flux. You need more membrane area. So because the higher flux, the more water is going through the membrane per unit time, that means that you're at a higher risk of fouling, because even if you have very pure water, there's probably a little bit of bacteria in there, there's a little bit of silt. So if you're processing more water per time, then you're gonna foul faster. It's sort of a matter of not necessarily when, if your membrane is gonna foul, but when. And so higher flux means higher fouling potential. Another advantage that operating a higher flux can bring you, though, is it does improve your permeate quality. Think of it as if more water is going through, it's sort of a tighter filtration. Maybe it'd be equivalent to having like a smaller micron filter if you're passing more water through per time. So it's a double-edged sword. You increase your risk of fouling, but you also get better quality water. And a higher flux also requires more feed pressure because you're just forcing more water through per unit time. So how you would calculate that is you've got your permeate flow, in this case is 80 GPM, and you're taking your total membrane area. So here we see we've got 400 square foot elements, and there's 35 of them. So we've got 8.2 gallons per square foot per day. So 8.2 GFD, 13.9 LMH. That's again more aggressive seawater design. So in our software, which we can get into a little bit later, we have recommended ranges for flux and recovery and all of these sort of basic parameters that you can follow as a rule of thumb if you ever move into RO system design. Just check for questions. Looks like we're okay.
Let me see here. For some reason I'm not changing, the slide's not changing. Let me see here. There we go.
All right, here we go. So I'm just going to touch on this one real quick before we move to our next slide. So this is how we would calculate average feed conditions. So this is sort of a tool we use to calculate salt rejection, which is something that Jerry touched on earlier. So if we have this process inside the pressure vessel where our feed water is getting more and more salty as you move down, the feed salinity straight from your pretreatment is not necessarily telling the whole story about what's happening in the pressure vessel. And so in order to calculate salt rejection and how the membranes are performing, we use what's called average feed conditions. So we can do one of two things. We can do a log mean or an arithmetic mean of our concentrate salinity and our feed salinity. and we get these two different values. And that's what we're going to use to calculate our rejection if we're doing maybe diagnostic work or thinking about just evaluating system performance after an installation or during a projection process. And that's going to make a little bit more sense on this next slide here when we talk about salt rejection.
For some reason, takes me a bit here to change it. Hold on.
No worries.
There we go.
So here's some terms that we're going to refer to a couple times just in describing how an RO element functions and how a system functions as well. Just a good thing to have a handle of and be able to do sort of quick calculator math with when you're doing system design. So salt passage and rejection are expressed as percentages of TDS that are removed by the RO process. You divide permeate TDS by feed TDS to get salt passage, the amount of salt that's making it through that RO element. Because as Jerry mentioned, it's a very fine filter, but in a seawater application with 30,000 ppm TDS, you might get 300 to 500 ppm through. That's still, several orders of magnitude of removal, but it might not be good enough for a certain client. So we need to have metrics for this removal, and that's why we calculate salt passage. And salt rejection is just, as a percentage, 100 minus this value. And salt rejection can be expressed at a system level. So the total amount in your permeate as a combined header, total amount in your feed, simple percentage of that. But we also use it as an attribute for a membrane itself. So a membrane is tested after we manufacture it, and that individual element has a salt rejection and then a flow. And when it's at scale, the rejection is different because it's repeated many, many times with different feed conditions within the system, depending on if it's a lead element in a pressure vessel or a tail element. So it's all, it's a matter of scale, but we use these terms salt passage and rejection to describe both system performance and membrane performance.
Oh. Is that the right slide there, Nate?
Yep.
Okay.
So we're going to move on to configuration now, a little bit more about how we put together an RO system. So the simplest array for an RO is single pass, single stage, and pressure vessels will be arranged in parallel, and they're all fed from a common header, as you can see here. The number of vessels depends on the production capacity, but it also determines the average flux, and therefore depends on the characteristics of the feed water, like we were talking about earlier. Permeate and concentrate from each vessel are collected in a common header, and the typical maximum recovery of this arrangement is 50% or less. Something I want to touch on real quick before we move on is you may commonly see pressure vessels that are 6 or 7 elements long. We work with, and you guys probably do as well, but we work with pressure vessels all the way from 1 to 8 long. And recovery of a system is largely dependent upon the length of the pressure vessel as well, because it determines how saline how salty the feed water is going to be in that tail element. So you might be able to squeeze another 5% recovery out of a single pass, single stage system if you have 7 element long pressure vessels instead of 6 or 5. These are not like hard, fast rules, which is why we use projection software, because each system is a little bit different. There's so many factors influencing if something is well designed or not. Okay, so multiple stage arrangement is a way to increase recovery by sending concentrate from one bank of pressure vessels to feed a second set. This is a type of design that can maximize system recovery while tailoring permeate quality. And this is very typical in brackish water applications where 2 to 3 stage designs can help to achieve 75 to 85% recovery. It's less common in seawater applications because you're dealing with very high salinity, and oftentimes industry standard is about 45% recovery. But in many seawater applications, a 2-stage design with an interstage boost pump can get up to 55 or 65% recovery. And in this case, permeate from all stages is once again combined into a common header. And something I want to touch on about the seawater application with an interstage boost pump is, in this case, we're dealing with aggregate concentrate from the first stage for a seawater application. So like Jerry mentioned, is going to be scaled up from, let's say, 35,000 ppm to 70 to 75,000 because of the recovery being 45 to 50%, you got to think all of that salt is going to be cycled up and expelled to the second stage. So the booster pump helps to add additional pressure for that second stage to overcome that difference in salinity and balance the flux across the two stages. Because you don't want to have a large inequality in the amount of water, the amount of flux between the two stages. You want to have relatively even amount of flow between the two. And a boost pump, as well as sometimes permeate throttling on the first stage, can help to balance that. That's something that we play with in software. But in this case is often a standard for two-stage seawater system. In order to improve water quality, permeate flow from a bank of vessels can be fed to a second bank or pass. And this lowers overall system recovery, but in a lot of applications, it's essential to achieve the necessary product quality. In seawater applications, two-pass systems typically provide less than 50 ppm TDS and boron less than 1 ppm. This allows for pH adjustment between passes as well. And in order to improve boron rejection, this is something we see a lot in seawater applications in, say, the Middle East or the Mediterranean. And oftentimes the second pass will treat all of the first pass permeate, but we can also use a split to treat only part of that permeate. So you can, put in a tea and send some of it around and blend it to create whatever product quality is required. And also that changes the size of the second pass. It's really like customizable thing that you can do. And so it's another variable that we play with to sort of tailor make the water depending on our client's needs. So like I mentioned before, this is a partial permeate split. And this is a little bit more of a complex way to dial in the water quality. So the feed end elements produce better quality permeate than the tail because they are receiving that pure feed water that's not yet been cycled up at all by the rejection process. So due to that average concentration effect that we observed earlier. So in a partial split, throttling valves or a blind interconnector between two of the elements are used to control flow, and the tail end permeate is sent to a second pass, while the feed end permeate is sent to blend with the final product water. And this is also something that can be, the percentage of which can be changed using various throttling techniques. It's something that's very customizable. You can change based on time of year, water temperature, and it just helps you to save energy, reduce the size of the second pass if necessary, and get the right quality of water for the right application. Something that's essential to consider in a case like this is fouling, because you are relying heavily on your lead element to produce high quality water. So you need to have a really dialed in pretreatment for a system like this.
Hey, Nate, if I could just interject here. I know some of the, I don't know if some of the guys online can corroborate this, but I've seen in the Caribbean, and you probably have seen around the world, that a lot of users take their tail membranes and move them to the front, like rotate the membranes just for the reasons you're mentioning. Their lead membranes are getting heavily fouled, so they rotate membranes through and maybe even dispose of the lead membranes.
Yeah, that's quite common. That's like a good practice as well. When you, a lot of these seawater systems will have a replacement schedule where they'll replace, 14% of their elements, so 1 out of 7 annually, let's say. And it's typical to take out the lead elements first because those are going to be the most fouled, and then to move the other elements forward and then install a new element in the tail, I believe is pretty standard. And that helps to sort of take the stress off of that lead element, and it's a good way to make the most of the new elements that you're putting in when you're replacing. But in absence of a replacement schedule, and where if you're just running your elements straight for 3 years, let's say, and you want to do a rotation schedule, it is good practice to move the lead element out and just change how that fouling stress is applied. It helps to prolong the life of the entire system. Okay, so concentrate or brine can be recirculated into a feed stream instead of being sent to the drain. And this is another method of increasing the system recovery. Basically, if you want to calculate total recovery of a 2-pass system, you can basically achieve 100% recovery with your second pass if you take that concentrate and recirculate it to the beginning of your system, because it's being absorbed into that feed stream. It's if recirculation does affect the salinity. So in a system like we have displayed on the screen, we're sending second pass concentrate to a first pass feed. And what that's going to do is have a positive effect. It's going to dilute the feed and actually give us better quality feed water in the first pass. But so often what we see in some brackish systems that are a single pass is we can recirculate concentrate from the first pass back into the feed in order to increase recovery. And that will actually increase the salinity of the first pass feed water. And so that's only a small percentage of your first pass concentrate can be recycled. Otherwise you risk increasing it to a harmful degree or to a degree that's not technically feasible. But in a two-pass application, it almost behooves the designer to include second pass recirculation because you're leaving water on the table that's really good quality. If not, for example, you're going to have pass one permeate that's 300 ppm, and you have pass one feed that's 30,000, and you'll have pass two concentrate that's 600 or 700. It's doing you nothing but good to bring that back into the feed and inject it, and then dilute your pass one feed stream. Okay, so a little bit about our software now. So Q+ projection software, which is pictured here on the screen, this is the main design window, is what we use to simulate our performance. And it has features to include every configuration I've described, as well as many other advanced features that help to create the most energy efficient design that can produce water quality that's optimized for any application. So I'm not going to review all of the software features today. It's a bit of a longer training, but our LG engineers are always available to host Q+ trainings, and we can sort of tailor fit those trainings to our clients' needs. So if you run wastewater reuse applications, we can think of some design examples and work through them together. And we can tailor it to a seawater application or brackish wells. It's a little bit more hands-on, and we like to do a little bit of pre-work where we come up with some examples, or we get some projects sent over to us ahead of time by an engineer. But I've heard from a lot of people that have gone through these trainings that our software is one of the most user-friendly, and people come out of these trainings with a greater understanding of how to design systems themselves, and really helps their throughput with getting out that technical information to their clients. So yeah, I cannot recommend using our software strongly enough, and I'm always available to train clients. I know that I've done a couple for Jess and other salespeople, but yeah, it's a very powerful tool. So as we mentioned before, feed salinity increases as the feed water moves through the pressure vessel. For this reason, flux decreases for each element in the series. So if we have a higher salinity for each element in the pressure vessel, then it's going to require additional pressure to push that water through. And so we have a decrease in flux from lead to the tail position. Now, good design will have a balanced flux as much as possible, since high flux can accelerate fouling. So we want to make sure that it's all moderate. It's to alleviate any fouling risk. Hybrid designs, like the one depicted in this chart, can achieve that balance by mixing lower flow elements with higher flow elements. So what we're seeing here is a design with all seawater ES, which is a high flow element that we have. That's the blue line there. And you can see we've got 20 GFD in the lead element, all the way down to 2 or 3 in the tail. And our hybrid design, we use some lower flow elements in the front and then finish out with some higher flow elements. And that helps to balance it so that we don't have quite as high of a fouling risk in that lead element. This is a technique we use a lot in seawater applications. Usually a single pass, but we see it in double pass a lot as well. A little bit more about hybrid designs here. They're not only intended to balance flux in the pressure vessel, they also ensure the lowest possible feed pressure while providing the water quality that's adequate to the client. So what this chart is demonstrating here is how the balance of feed pressure and product water quality helps to illustrate which combinations of elements are best for a particular application. So what we'll do if we have a request from a client is we'll put together multiple options, and we want to optimize where the water quality is sitting. We want to sort of with a margin of error, we want to cut it close to that requirement and not provide water that's too pure for your needs, because then we're using excess feed pressure. So we want to optimize how much energy we're spending to make just the quality of the water we need. And I will add that hybrids in seawater usually mix elements within a pressure vessel, but in brackish water, we'll use hybrid designs sometimes. And typically, the elements in one PV pressure vessel will be the same, and then we might use a different element type in the second stage. And that's more of a balancing flux type thing. We might use a high rejection, low flow element in the first stage, and then a higher flow, low energy element in the second stage. Just a design option that we might use.
Okay, I think Nate, I don't know if you're going to get into more product selection of LG membranes here, right? So what's coming
Yeah,
next?
this is the next slide. Yep.
So we really want to be, we just want to, just in all fairness, LG's here, and thanks for their time and their input. When you saw what Nate showed in terms of software, most, I guess all membrane manufacturers have a software. I do have to say though, the LG is easy to use. I have to say that, but it is worth, you can get those softwares from any manufacturer. You may have LG membranes, you may have Dow, you may have Hydronautics, and they look overwhelming when you first get them because I play with them. But when you get in there and dig into them, they are really interesting, and you do learn a lot. What Nate was just talking about is mixing in different models within a pressure vessel, within a system. That also works. And I think he's going to get into now, but I'm going to ask you, Nate, just to go through it pretty quickly. A little bit more about the product line of LG, but in all fairness, they are a great membrane producer. I'm going to be honest, but there are others out there as well. So we'll move forward.
Yeah, so what we've got here is not the entire range of elements we have available. This is just sort of the nomenclature that we use, so you can familiarize yourself with it.
I'm going to interrupt though again. I think though this is very useful because if you notice in your membranes of those that are listening, you're going to see these things and maybe you didn't even know what they meant before, but SW and BW, most manufacturers use that. That's just designating a seawater or a brackish water membrane. In the case of LG over here on the right, we've got ES, that's energy saving. Dow, I think, calls it LE, low energy. So there is information in the name, in the product name of the membrane. Nate obviously is showing his, but your other brands, the same thing, almost all of them. Hydronautics, not so much. I never understood CPA and all that. But the Dow certainly, part of the name tells you what the membrane does, and same thing with LG. Go ahead, Nate.
Yeah, so like Jerry was saying, this is not our entire product line, but this is a little bit about the nomenclature and where we place it on this sort of high to low spectrum for the couple of these parameters. So mostly this is referring to feed salinity and product quality here with these. So we've got seawater ES and BWES. That's energy saving. Those are our high flow, low rejection elements. We've got seawater R. The R is just for rejection. That's sort of our flagship seawater model. And then we've got seawater GR, which is great rejection, and seawater SR, which is superior rejection. Those are our lower flow, higher rejection elements, and we use those in sometimes a single pass or something with critical boron rejection. Those are going to be your higher pressure applications. And then on the brackish side, we've got BWR, which is our higher rejection brackish element. And then our recently released BWR-G2, which is seeing a lot of installation recently. It's just the next generation, which has got higher flow and higher rejection. Something that's not mentioned here because they don't really fall on this spectrum of low to high, let's say, rejection and flow, is we also have a fouling resistant BWAFR, which has a coating on the element for use in high fouling applications. So, if you have higher SDI or if you're just in a wastewater application, it also only comes in a 400 foot square variant with a thicker fouling resistant spacer. And we also have our BWR Dura, which is coded for chemical resistance. So if you have an application that uses frequent chemical cleanings, that's something that we can use. But these are spec'd out very similar to our BWR, where they just have that standard high rejection performance, but they have tailor-made characteristics to the membrane that make them suitable for more aggressive applications, let's say. But yeah, again, typically we'll go into the catalog more in depth if we do software training with clients. I don't want to take up too much time. This is the last slide I have, but yeah, just giving you a little bit of a taste of what we have on offer. And there's a almost limitless combinations of what you can do with projection software and with all the models we offer. So we're always here to help, and obviously here now to answer questions.
Hi, ladies and gentlemen. Do you have any questions? Feel free to unmute your microphones and place any questions you have. I think somewhere in the chat earlier, there have been a few questions already answered in the chat room by Jess.
We can cover some slides too if they want, Ignatius.
Yeah. But I thought it was a pretty comprehensive presentation with the three of you out of CaribDA. And I imagine some of it is kind of new to some of our operators who are dealing with surface water most of the time. But as some of them may be gravitating gradually into desal systems, it is good that they can get a basic understanding of what our systems are all about. And I guess a good refresher for some of our guests out of the Bahamas and some of the islands where they use desal systems. Any questions? Well, if there are no questions forthcoming, I'd like to thank the team of CaribDA, Caribbean Desalination Association, of Jerry, led by Jerry Matteo, of WaterTech Sales and Consulting, Inc., Jess Salvador of LG Water Solutions, LG Chem, and Nate, who led us through the second half of the webinar. I want to thank you very much for giving us your time and sharing your knowledge with us. And we'd like to especially thank the president of CaribDA, who is also following the webinar, Mr.
Ignatius, thanks for having us. We really appreciate it. I don't know, your constituents may or may not know, I think CaribDA and CAWASA were just forming a really nice partnership in a lot of ways. This is one you invited us to present here, but I really like what we're going to start doing with membrane operator certification. So those of your members that are running RO systems, I think the Bahamas already knows, and some of the others may know, that we're offering, CaribDA's offering a training course that leads to certification for membrane operators, and CAWASA is going to actually do I guess the exam and certification part. So it's a real, because that's, you already have the organization geared towards training and certification. We've got the technology on the membrane side, so it's something we're really looking forward to. COVID held us back because we have a couple of utilities already interested that we're hoping to do training this year. Bahamas went through some last year, and we're looking forward to working with CAWASA on that program and others as we move forward.
Yeah, quite right. Last year we did have a good program. Started with the Bahamas and partnership with CaribDA, and offering the certification program, so that we sort of endorse the certification, as we are one of the certification agencies for the ABC, American Boards of Certification in the Caribbean. And we are looking forward to continued partnership with CaribDA. Unfortunately, COVID took its toll on a lot of activities. We also have coming up, I think next month, the CWWA, were to have hosted their conference in St. Lucia, and that too went under. But they're going to continue it via virtual means. So I look forward to connecting around the CWA virtual sessions in the coming month. And I would also, I think Janet was also present. I don't know if she's on, and I'd like to thank her for helping to coordinate your participation and the presentations by the CaribDA team. So I know it's been, and of course you have gone into extra time, and that was pretty good because it's a lot of information. As I said, we are recording it and we are going to circulate it to all of you, all the participants and the presenters as soon as we're through. So thank you very much, Jess, Nate.
Thank you.
And Jerry.
Thank you, guys.
Thank you.
Yeah.
Thanks for the invite. Let's do it again next time.
Yeah, thank you very much. And have a good evening, everyone.
Okay.
Thank
Good
you.
evening.
Bye, everybody.
Thanks again from the Bahamas. We appreciate the invite.
Yeah, you're welcome. Good to have you around.
Follow up from what we did.
Yeah.
Unfortunately, we couldn't have those follow-up exams, but we continue to see how we make it happen.
Yeah.
Good presentation today.
Okay. Okay, cheers. Bye-bye.
Okay,
Okay.
everybody. Bye. Thank you.
Cheers.
Good.
Bye.